Let's take a look at another example for finding type 1 error, type 2 error, and beta. So let's read the problem. A consumer products company is formulating a new shampoo and is interested in foam height that it develops in millimeters. Foam height is normally distributed and has a standard deviation of 20 mm, and the company wishes to test the following hypothesis. The null hypothesis H naught is that mu is exactly equal to 175 millimeters, and the alternative or the research hypothesis H1 is that mu is greater than 175 millimeters, and they have a sample size of 10 samples of this product. And the first question is to find the probability of type 1 error if the critical region is x bar being greater than 185 millimeters. So let's kind of consider this problem for a second. So here we are looking at a one-sided alternative hypothesis, given that we are looking at H1 being mu greater than 175. So in fact, we're looking at what is called an upper tailed hypothesis or an upper tailed test. If this is less than, it becomes a lower tailed test, and if it is not equal to, it becomes a two-tailed test, and that's an example that we looked at earlier on in the previous video. So let's see what kind of questions are being asked. The first question is find the probability of type 1 error if the critical region x bar is greater than 185, and the next one is finding the probability of a type 2 error if true mean happens to be mu equals 185. So if you recall, the mu we assume to be 175 here, so here in fact we are saying mu is 185. So how do we compute the type 2 error? And then find the power of the test, which is 1 minus beta, and I'm asking you here to solve using both by hand and by using Excel, and I'll show you how to do this using Excel. First, let's take a look at how to solve these problems by hand, and so let's get into it. So type 1 error, looks a little bit lighter, but I hope you can see this. So type 1 error, so what is a type 1? First we need to understand what the type 1 error really stands for. Alpha is nothing but the probability of rejecting the H naught when it is in fact true. So that is a type 1 error. So since we are considering a one-sided hypothesis, so anything that falls beyond 185 is the rejection region or the critical region, and anything below 185 is the acceptance region. And sigma has been given as 20 and number of samples is 10. So that is the data that is given to us. So how do we compute alpha? So alpha is really the probability that x bar is greater than 185 when mu is equal to 175, because that was the hypothesized mean, and this is our rejection criterion, being greater than 185. And since alpha or the type 1 error is rejecting the H naught when it is true, so we have to compute it this way, just like we did it before. So the probability, we can standardize this normal distribution. So x bar minus mu divided by sigma over root n is greater than 185 minus mu divided by sigma over square root of n. And if you substitute for the values, we can compute probability that z is greater than this component right here, and when you simplify that, that turns out to be 1.58. So instead of finding a z greater than, you can also do 1 minus z, probability that z is less than 1.58, and that happens to be 0.057, or in other words, we have a 5.7% chance of rejecting the null hypothesis when it is in fact true. So I hope this example kind of gives you a better idea of how to deal with one-sided hypotheses. Now let's move on to finding the beta error for this particular problem. So finding the beta error, so first let's define, so I want you to adopt a stepwise approach when solving these problems, because it really helps you to formulate the equations and get the concept correctly. So beta is nothing but the probability of failing to reject the H naught when it is false, or in other words, you're accepting the H naught when it is in fact false. So that is your beta error. So in this case, when do we fail to reject it? If you see that a x bar is less than 185, then you fail to reject it. And here we are also being given that the mu is also 185, not 175 anymore. If you recall, I'm just going to go move up here. If you remember, mu here was 175 for the alpha error, but they have found that the true mean is in fact 185. So that's the reason you have this mu equals 185 in this case. So if you once again try to standardize this expression, we will get probability that x minus mu divided by sigma over square root of n is less than or equal to x bar, we know is 185, and mu is also 185. So obviously this becomes 0. So if you actually look at what value of in the z table gives you, or z of the z-score of 0.00 is zero point 0.5, which means that there is a 50% chance of failing to reject the H naught when it is false. So clearly the power of the test is very straightforward. Power of the test is 1 minus beta, so that is 1 minus 0.5, which also happens to be 0.5. So all that really means is that this hypothesis test is only 50% effective in detecting the true mean if it is 185 mm. Okay, so that is how you compute the alpha error, the beta error, and the power of the test. So what we will do is we will solve the same problem in Excel, and we'll compare our solutions, and and also we'll be moving forward after this to actually applying the hypothesis testing procedure, because so far we haven't really tested any hypothesis. We are simply looking at calculating the type 1 error and type 2 errors and the power of the test for a given hypothesis, given that we have there is a stated acceptance region or a rejection region. But in traditional hypothesis tests, you might be able to you would have to actually accept or reject a hypothesis based on a certain level or a certain level of significance. So this acceptance region might not be given to you, but we'll still be able to make decisions on the hypothesis, and we'll take a look at how to deal with those issues.